Hello everyone. Today we will discuss X-ray diffraction, which is a very important material characterization technique. X-ray diffraction is a versatile, non-destructive analytical technique which is used to analyze physical properties such as phase composition, crystal structure, and its orientation in the powder and a fully dense solid sample. As you can see in this picture, the incident X-rays produced by the source illuminate the sample, and in the sample we can see that whether it is a powder sample or a fully dense solid sample, we have a unique arrangement of atoms in that sample, and there's unique spacing between these atoms, which is known as d-spacing. Now XRD machine is capable of measuring a d-spacing between these atoms. These atoms can be from different elements or different compounds that can be formed in the sample, and when the incident rays they will interact or illuminate on these atoms, they will diffract at certain angles. This XRD machine, by moving the tube or a sample and a detector to change the diffraction angle, this XRD machine will measure the intensity of the diffracted X-rays and also the angle between the incident ray and the diffracted X-rays. And in this case, the diffraction data will be recorded. Now, I will show you why do we need XRD analysis on different alloys. So this is a scanning electron microscope image of a magnesium alloy. In this particular magnesium alloy, zirconium and strontium they were used as alloying elements. Now you can see that in this figure, SEM image, we can see a grain boundary of this magnesium alloy. And around this grain boundary, we can see that there is another phase which is forming around the grain boundary. This is an intermetallic compound. So because this magnesium alloy contained zirconium and strontium as alloying elements, so these elements can react with magnesium during the processing. So they can form magnesium strontium compounds or magnesium zirconium compounds, and similarly other compounds. Now XRD technique, it can give us a very useful information about identification of different phases that may present in similar alloys, and also their crystal structure and the orientation in this alloy. All of this information can be obtained through XRD analysis. Now I will show you some videos which I have recorded on an XRD machine at RMIT University, how we can prepare the sample and how we can mount the sample for XRD analysis, and then I will move on to analysis of the XRD data that we actually obtain after this experiment. So here you can see that these are the sample holders and the sample discs of magnesium that we can actually fabricate, and then we have to mount in these sample holders. So how we actually put the sample? So we use a blue tape or a gum to actually stick these samples in the center of these sample holders. We have to make sure that all of this blue tack or the gum, it is underneath the sample. It is only for the sticking purpose. And one thing we have to make sure we can do it through the glass slide, that the top surface of the sample that we are going to run on the XRD machine, it is parallel to the edges of this sample holder. So we can do it through this glass slide. So this is how they look like. All three samples or as many samples you can prepare. They are ready for the XRD analysis. Now this is the XRD machine at RMIT University, which is Bruker and Dever model. So in this machine, we can mount 66 samples altogether, and they will be in a queue and they will be running on this XRD machine. So we have a software with XRD machine, so we can specify the positions on which our sample is mounted, and we can make a program like the diffraction range, where normally we do it from 10 degree to 90 degree. We can specify the step size, how fast this will be scanning, and we can also provide some other details about the XRD technique, whether the sample it will be rotating or it will be static, and all of this information is provided in the software, and the machine will follow the program and it will run the samples one by one. So in this machine, this particular model Endeavor, we can actually mount 66 sample altogether. All right, so now I will show you. So once we complete the XRD analysis, the sample, the machine will actually complete according to the program and provide us a raw data file. So this data file will actually record the different angles between the incident X-ray and the diffracted ray, and also it will measure the intensity of diffracted X-rays. And once the program will finish, then it will provide us a raw data. As you can see in this Excel file, the first column is angle, and then we have a second column of the intensity. Okay, and you can see that if we plot a graph, then we will have a XRD spectrum like this. So all the analysis is done on an offline software. Normally, EVA software is used to do a data analysis on this spectrum, which is obtained from the XRD machine. Now, when we use that software, EVA software, what we do actually, we actually provide this software some information. What different elements were used in this magnesium alloy. So we will use magnesium as an element, we will use zirconium as an element, and we will also provide information about strontium. And then we will actually do scanning and matching on this XRD spectrum, which was obtained after running these samples. So this software will actually then do indexing, and it will try to match these peaks with different possible compounds, because this software has inbuilt database, and then that database will be used to index or each peak that is actually it can be viewed in this spectrum. So what I will do, I will copy this column, and normally I do this analysis uh, in Origin software. So I will show you how to do it. We can also do this in Excel, but normally I use OriginPro for this data analysis of XRD spectrum. All right. So we can paste our first column here. This is angle, and now I will do the count. There we go. And then I will just select both of these. So on the x-axis we have angle, and the y-axis we have the intensity of the diffracted X-rays. So by clicking this line, I will actually plot a graph. So I can reset the scale on the x-axis, just double click it, go to scale. I did it from 10 to 90 degree for this program. So I will choose 10 to 90 degree. Here, the angle was 2 theta. So, and I right click here to select a symbol map, and I choose theta from this symbol. And the units of this diffraction range were in degrees. Similarly, on the y-axis, I had unit of intensity, and this intensity had an arbitrary unit, so I just probably keep it like this. Okay, so in this way, I can also do one more thing, increase the width of the line so we can see things clearly, and we can connect it using B supply to have more clarity. And you can see we have now very smooth XRD spectra. We do not need values of intensities because this is in arbitrary units. Now we can do one more thing. We can do lines and ticks to close the box. This is normally what I do for a better representation. No tick marks on the top, so you can see that it's here. We need one more on the right, so here we go. Show lines and ticks. Now this is just like a formatting. It's not very important, but it's for like a good data presentation. On the left side, I do not need any uh, ticks, major ticks or minor ticks. So there we go. All right. So now we have our data with us. We can do one more thing on the horizontal axis. We can refine this scale 10 to 90 degree with the increment of 10 degrees. So we can easily see which peak is on certain angles, right? So we can see that we have a peak at around 24 degrees, then we have something around 27 or 28. Yeah, it's 29 actually. Then we have other major peaks of magnesium. All right, so right now the XRD machine will provide us this data. We will do scanning and matching by using the information about the material. Like for in this example, we have magnesium, zirconium, and strontium, right? And then the machine will provide us that software that we are using. It will provide us information about the magnesium peaks and magnesium strontium phase that can be formed in this alloy. All right. So in the folder, when we do the scanning, the first thing that we will actually make is uh, the peaks information. What are the angles? How many peaks we have identified? So I will open this XRD file, PDF file, and we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 peaks that we have identified, and their angles they are indicated on that. And if we go down, this PDF will be generated, and we can see that all the peaks information, their angles, and their d spacings, which is in angstrom. So 1 angstrom is equal to zero point 0.1 nanometer. So if we divide this value, which is 3.674 by 10, it is 0.367 nanometers. So it means the peak, which is at 24.20, it is coming from the some compound or some phase which have in which the atoms they have a d spacing of 0.367 nanometer. It is a very useful information because if we further characterize these alloys by some other techniques like high resolution transmission electron microscopes, in that we can also use electron microscope to do a diffraction of electron beam, and we can also obtain similar information using that machine. So we can see that if we create a it can we can actually view a lattice at high resolution with a d spacing of 0.367. So these two many characterization techniques they actually complement each other. So you can see that from XRD machine we obtain the diffraction angles, and we also have information about their corresponding d spacings. So now we know that we have a peak at 24.204, then we have 29.47, 32, and similarly we have peak at 81 degrees, right? So next thing up is we have identified that some of the diffractions they are coming from the magnesium peaks. Now the magnesium is blue in color in this one, so we can go to this one. So we have number of peaks which can be corresponding to magnesium. So we can see that 32.173. So this is the first peak for magnesium. So we can have a look on our own. So this one is coming from 32, or yeah, if we go back to our original uh, peak search, like all peaks. So we have 32.23, which is very close to the first peak of magnesium. So we can easily tell that, okay, now this peak is coming from magnesium. So what I will do, I can write, I can create a text, go to symbol map, choose some maybe symbol, maybe this one, and I can put it here, and I can tell that this is a magnesium phase present in this. This peak corresponds to magnesium. Then we have the second peak, which is coming from 34 degrees. This one 34.458, and if I go back to uh, that magnesium peaks, we see that 34.385 also corresponds to magnesium, which has a d spacing of 2.6 angstrom, means 0.260 nanometers. So I will just copy this one, paste, and this will also be telling me that this is from magnesium. And similarly, the third peak, which has a high intensity, I go to my all peaks file, and I see that after 34 we have a peak at 36.661, and it also corresponds to magnesium. If I go to magnesium peaks, I can see that 36.60 is also a magnesium peak. There we go. And then we have a peak at around 47.89. I will go to my all peaks file, and I can see that after 36 we have peak at 47, which corresponds to magnesium, as we can see here. So I will copy this symbol, and I just bring it here. And similarly, I have, if I look, keep following this procedure, I can see that there are other peaks which corresponds to magnesium, and we can look at what we have to do. We have to see all peaks like 57.416 and see if they match the magnesium, as we can see here 57.36. After that we have 63. So in all peaks we can see that we have a peak at 63.156. So in this way we will label all the peaks. All right. And one thing more, we can see that we have two small peaks here, which is around 24 degrees. So we can see that magnesium peaks here, which is magnesium peak, it is not coming from 24. So we have to look at the other phase as well. So if I go back to my folder here, so we can see that we have another phase, which is magnesium 17 strontium 2. I will open this one. All right, so we can see that it is in blue, this magnesium 17 strontium 2 phase. So I will go to my blue icons like this one, and here I can see that at 24 degrees it has a d-spacing of 0.369. I will zoom in so that you can have a look. 24.099, it has a d-spacing of 0.369. So it means in my XRD spectra, this peak here, I will zoom in. So this peak here, it is coming from uh, this phase. So I will change the symbol for this one. So I will go to symbol map, choose something else, maybe this one. All right, so we have this phase here, and we have this phase, another phase here. So both of these phases are coming from uh, magnesium strontium compound. So this was the compound which was actually forming around the grain boundary. Okay, so this one was at like 29.41. So if I just zoom out and if I go down, so I can see that uh, here it is magnesium 17 strontium 2, and we have a peak at 29.4 degrees, right? So it means that this one also corresponds to, this one is like 29.4, so it corresponds to this magnesium 17 strontium 2, right? So and similarly we have other peaks that will be actually, we can use all peaks, then we look at what is the diffraction angle. And for example, if one we have one peak here, we will try to fix this one. Okay, now this peak has a diffraction angle which is around 61.88. So we can see if we have this peak here 61.88, so it is very close to this one 61.8. So it has a d spacing of 0.149 nanometers, right? So what we will do, we will just copy this phase from here and put this one here. Okay, so it means that this peak corresponds to uh, magnesium 17 strontium 2 compound. All right, and similarly we will do for this phase, this peak, this peak. Okay, let's do it. This, we have a peak at 72.64. Do we have 72.64 here? So let's have a look at magnesium. So this is magnesium peak. So 72.4, this is closest, so it is 0.130. So this peak is most probably coming from magnesium. Yeah. Then we have a peak at 77.88, which is coming from here. It is also magnesium. If you do not find this one at magnesium, then look at the other compound, other PDF that we have generated for the other phase. So we make sure that all the peaks are indexed. Then we have peak at 79.64. So we look at the other one. So it's 79.4 is from the other phase, which is uh, magnesium 17 strontium compound. So we just copy this one here and put it here. So it means when we do this, it means that all the possible major phases in this XRD spectrum, they are done. So the only thing left we will do is we will actually create a legend so that we know which symbol belongs to which phase. So I will just bring it here. Then I will go to my text section and I will just write magnesium. And then we have this phase here, this symbol. It corresponds to the other phase. So I will copy this one, bring this one here. So I will write magnesium 17, strontium 2. And I will make them like a subscript, and there we go. So it means that this symbol corresponds to magnesium and the other symbol corresponds to the other compound. One thing extra we can do in XRD analysis, if we go, for example, if you look at this peak, the magnesium peak, which is at 32 degrees. So I will show you one more information we can get from this magnesium peak, which is at 32.173. It gives me the angle, diffraction angle, the d spacing of this of this phase, which is magnesium at this refraction angle, and it also give me a value of HKL 100. So these three numbers, they provide a very useful information, and these are known as Miller indices. It is a group of three numbers that indicates the orientation of a plane or set of parallel planes of the atoms in a crystal. Okay, so we in this with these three numbers, we actually obtain the orientation of the crystal in that atom. Okay, and it's a very useful information. So what we can do, 32.173, if I go back to my XRD here, so I can just create a text here, like, and I will provide this number 100, like this. Okay, and I go back, take it back to that phase, and if I double click here, so I can, yeah, I can rotate this one, and I will just bring it on to the right number. Okay, similarly we have the second magnesium phase coming from the 34.44, so it is coming from here, and it has 002. So I will also indicate the Miller indices of each diffraction of each peak, 002. And the third one is the strongest line with 100% intensity, the biggest one. Has 101 orientation. So 101. There we go. The fourth one, it is at 40. It has at 47 degrees something. Yeah, 47. So here we go. It has 102. There we go. Uh, the other one, it is at 57. It has 110. Then we have at 63, it has 103. There we go. Then we have at 68, 112. All right. After that, we have at 70, or it is close to 69. It is 201. It's very close, so I will just take it maybe here, so you can correlate. That is, yeah, it is 201. Okay, then we have at 72 degrees, which is 004. There you go. The last one for magnesium, it is at 77.7, which is 202. And similarly, we repeat the process for the other phase, which is magnesium 17 strontium 2 compound. Okay, so the first peak, it is at 24, and if I zoom in, we can see that for this one, which is 24.4, I will go down because the PDF generated this information here. I do not have this HKL for, unfortunately, I didn't record it. But when we have this analysis, most of the peaks are coming from magnesium. So it is important that we provide this crystal information. And normally we also record it for the second phase, but in this example, the PDF I have, it doesn't have this HQL values, unfortunately. For I will have a look in the other file if I have it here. Yeah, for the first peak I do not have, but for the second peak it recorded a value of 112. So I can just put it there, 112. So what we actually do with the XRD, we actually try to provide maximum information about the phases. Number one, it is the most important information, which phase, at what angle, and then we can also provide information. This is a secondary information that we can provide, that what is the Miller indices of, or the orientation of the crystals on this plane. Like what is the orientation of a plane or a set of parallel planes of atoms in a crystal. So this information can be actually obtained through XRD analysis. Okay, so as I will go back to my figure where I provided example. So this XRD spectra was actually obtained from this particular magnesium alloy. So we can see that around the grain structure we have this secondary intermetallic phase of magnesium 17 strontium 2 that was actually found on this one. And from the bulk material we can see that most of the peaks were coming from the magnesium alloy. So these two phases were dominant in XRD spectrum for which was obtained from this particular alloy. Okay, for a reporting purpose, what we do, same thing we can also do in Excel, but I normally do it like OriginPro because it's very easy and we can make very good graphs which can be published in research articles. So normally we can convert them in figures. Like I can export this graph. Okay, I will export it in JPEG format. File name I will write XRD spectrum for magnesium zirconium strontium alloy example, and I will provide a path where I want to save it. So for this exercise I will just save it in mm, maybe in downloads. Yeah, I can preview it. Okay, so yeah, this is okay. Change the path, maybe go to desktop. Okay, so now I'll try to find the not open the file. Okay, I need to change the path. Maybe I just do it in some folder. XRD polysamples. Okay, just do it here. Okay, I will try to find it now. Okay, so if I go to, yeah, okay. If I go to folders like XRD polysamples, so I can see this graph here. Yep, here you go. So you can see that we have created an image. So we have to just to provide the format of the figure, like it will be in JPEG or TIFF format. The resolution, it is generally default value is 300 dpi, and we provide a path, the name of the file, and it will be saved on your computer. You can save it in your on your desktop or any. You just provide a path, and in this way you can create this image JPEG, and then it can be used in your reports, or it can be used in research papers, or wherever you want to use it. So from this example, what we have seen that we can identify the phases based on the spectrum that we'll obtain from the XRD machine, and then we will try to index it. So how do we index it? We try to do scanning and matching in EVA software by providing the information about the elements like magnesium, zirconium, and then strontium, whatever is the composition of that alloy. And according to this information and the spectrum, this software will try to match each peak with the possible phase. Okay, then it will generate these PDFs from its database. So we will have information. First information is about the peaks without any phase information. Okay, all peaks. So all peaks folder means we have identified, for example, 16 peaks in this spectrum. This is the very first information. The second information is like we have indexed with magnesium phase. So for example, 34 degrees, 36 degrees, 38 degrees, etc. It is coming from magnesium. So we look at the value of the 2 theta, which what is the angle, and we try to see whether this is coming from magnesium. If it is not coming from magnesium, then we go to the second PDF, which is generated by the other intermetallic phase, which is magnesium 17, strontium 2, and we try to index it, provide different symbols so that we can easily distinguish which phase and create a legend in this figure, so we can obtain this information. Extra information that we can provide is the orientation of atoms in a crystal in the form of Miller indices. That is also provided in these PDFs from magnesium and the other compounds. So similarly, if we are using like it is a tertiary magnesium alloy with several other uh, alloying elements, these alloying elements can form different types of other intermetallic compounds. So we will generate PDFs from the database. We will try to scan and match, and then we should follow the same process to index each peak in this XRD spectrum. I hope this example you will find it useful, and it will help you to index the XRD spectrum, or different XRD spectra that you will generate from the XRD machines. Thank you very much.